Hi, in this video we start implementing the binary search tree data structure together. So first of all, let's create a new Java project with the name, for example, binary search tree. Okay, and in this binary search tree I'm just going to create a package, for example com.myname.binary search tree. We usually use this BST instead of binary search tree, whatever. I'm just going to create approximately 4 classes, the app.java, from where we are going to test our application. Then we are going to have a node. This node is going to represent the nodes in the tree-like structure. Then we are going to have the binary search tree. So the binary search tree. We are going to have a tree interface. In this interface, we are going to define the behavior of the binary search tree. The binary search tree is going to implement this tree and going to implement the methods defined in this tree interface, basically. It is a good programming practice in object-oriented programming languages to program to an interface or a supertype. So we are going to instantiate a binary search tree as a tree, and the tree is an interface. So basically, if you take a look at, for example, ArrayList, we usually do not instantiate ArrayList like this. For example, list is equal to a new ArrayList. We usually use the list interface instead. Why is it good? Because it's going to be much more dynamic. I'm going to import it because if we come to the conclusion that array lists are not going to be the perfect underlying data structure for our application, we are able to change it to a linked list without any problem. I think that we will have, okay, linked list, sorry for that, linked list. Okay, so it's going to be much more generic in the sense that we are going to program to an interface and we are able to change between array list and linked list without any problem. Okay, so this is what we are going to do here. We are going to have a tree interface, and in this tree interface we are going to define the basic behavior. We would like to traverse the binary search tree. Of course, we would like to public void insert, and we would like to make it generic. So I would like to insert some generic data. Of course, we have to use this t parameter. And I'm going to have a public void, for example, delete. I would like to get rid of the data. Then, for example, I would like to find the maximum. So get max. It's going to search for the node with the maximum value and going to return the content of this node. And I'm going to have a t get min. It's going to return the minimum item, the minimum node with the minimum value in this binary search tree. Okay, then what about the node? The node is going to represent the nodes in our binary search tree. So basically it's going to store some generic data. Of course, to be able to store the generic data, we are going to make this node generic. Okay, you may pose the question that why is it good? Because we would like to use it for strings, doubles, integers, custom objects, whatsoever. Basically, all the collections related data structures in Java are implemented as a generic data structure in the sense that, for example, in an array list, we are able to store integers, doubles, UI-related components and custom objects. Okay, this is why it is implemented as a generic container. Okay, so I would like to store a reference to the left child, because basically in a binary search tree, every single node has 2 references. A single reference for the left child. The left child is going to contain the values smaller than this given node, so the parent, and the right child. The right child's value is going to be greater than the actual node value. So it's going to have a node t, for example, right child. Okay, in the constructor, it's going to get the data itself, and we just have to set the data. So this.data is equal to data. And I'm going to override a toString method, which is just going to return with this.data.toString. Okay, maybe you pose the question that why is it good to override this toString method? Because whenever we print out an object, for example, we are going to make the system out println, and we called, for example, on the left child, Java is going to ask that, okay, it is an instantiated class. Okay, so what should I print out? The data, the left child, the right child, or whatever. And this is why we override the toString method, because whenever we're just dealing with this given object, Java is going to know that, okay, we have to print out the data. Okay, so basically this is why it's good to override this toString method. And I'm just going to generate the getters and setters, so the data, left child and right child. Okay, Ctrl-Shift-F to auto format, and basically that's all about the binary search tree class. So it's very important that in our implementation, we are going to have a given node. A given node is going to store a reference to a left child and a right child. The left child's value, so the data in the left child, is smaller than this given node data, because inside this left child it is a node as well, so the left child is going to have a data as well. So the left child's data is smaller than this node's data, and the right child's data is greater than this node's data. So this is how a binary search tree is constructed. This is what we have been discussing in the theoretical section. The left subtree containing items smaller than the given node, the right subtree containing items greater than the given node. Why is it good? Because if we construct a data structure like this, we are able to achieve logarithmic time complexity for most of the operations. Okay, so in the next video we are going to implement these features one by one. Thanks for watching.